There we go. So as you'll all hopefully recall, alcohols are one possible organic derivative of water, by which I mean that if you take away one of the hydrogens of water and replace it with an alkyl group, you've got yourself an alcohol, rather. And of course, so ROH essentially, and of course the R cannot be hydrogen because then you'd have water. Water is inorganic. Phenols are a special kind of alcohol in which the R group is a benzene ring or a substituted benzene ring. And they have some similarities with alcohols and some differences, which we'll actually start to get to today. Both alcohols and phenols and thiols also, which is the sulfur analog, are SH instead of ROH. All three of these show up all the time in biological processes and in living systems. We'll learn next term about carbohydrates, for instance, which basically are aldehydes or ketones with a whole bunch of OH groups stuck all over the molecule every which way. So they're just polyhydroxyaldehydes and ketones. So in order to know what you'll need to know eventually about carbohydrates, both in this class, well, in organic 2 and in other classes, you need to know something about alcohols in order to understand all that. You'll see alcohols and related compounds in biochemical pathways like glycolysis and the Krebs cycle. And also you'll find alcohol functional groups, I should mention, in certain amino acids. They were serine and threonine and tyrosine. Tyrosine actually is a phenol. And also in many pharmaceutical compounds, both over the counter and by prescription. The simplest alcohols are, of course, methanol and then ethanol. Methanol is the only methyl alcohol. So that's the only possible alcohol with a methyl group. That's the smallest possible alcohol. And again, you can call that either methanol or methyl alcohol. Both are perfectly acceptable names. After that, you start getting into the 3 other flavors of alcohols in general. But again, there's only one possible alcohol with a methyl group. Alcohols of this type we call primary alcohols. So R is any alkyl group here. If our alcohol has 2 R groups attached to that carbon, call them R1 and R2, then you've got yourself a secondary alcohol. And last but not least, if it's all R groups, and these R groups can be either the same or different, doesn't matter. But if there's 3 alkyl groups directly attached to the carbon bearing the OH, now you've got a tertiary alcohol. And I think a quick glance will confirm to you that there could be no such thing as a quaternary alcohol, right? As soon as you form another bond to an alkyl group, you can't have the OH and it's no longer an alcohol. So those are they. Those are essentially the 3 types of aliphatic alcohols. Aliphatic meaning that they're substituted with alkyl groups. And so besides methanol, I think you'll find all of the other alkyl substituted aliphatic alcohols fall into one of those 3 categories. They'll be primary, secondary, or tertiary. And as you can imagine, primary, secondary, and tertiary alcohols have a lot in common in terms of their reactivity, and there also are some important differences, which we'll get to as we continue in chapter 17. What else can we say about alcohols? I think I'll leave nomenclature of alcohols for you to practice on your own. There's plenty of opportunities to do that in the chapter 17 OWL assignment. However, I don't think anything there is going to knock your proverbial socks off with your shoes on. There's nothing too surprising. If you can name alkyl halides, then I think you'll find it's not a big problem to name alcohols. And you'll use that ol ending, OL, signifies that you have an alcohol functional group. So but I don't think you'll find that to be a tremendously hard challenge. Certainly alcohols are quite polar like water is. Certainly they have the same geometry as water. The oxygen will be sp3 hybridized. So it's like the oxygen sits at the center of a regular tetrahedron, and at two of the corners of the tetrahedron, or rather two of the corners of the tetrahedron, you'll have the bonds to the oxygen going, one to hydrogen and one to an alkyl group. And then at the other two corners of the regular tetrahedron, you'll find the two non-bonding lone pairs on oxygen. So it is a bent geometry, just like the oxygen water. But you could still say that the overall VSEPR geometry is tetrahedral, right? There's really only three VSEPR geometries that we'll ever use in organic chemistry: linear, trigonal planar, and tetrahedral. Every atom is going to be built on one of those three templates for us. And yes, okay. Well, that's good news, I guess. Yes, I'm sure. All right, goodness. Oh. Well, thank goodness for that. Okay. So where was I? We were talking about the geometry. Oh yeah, all of the central atoms we're going to run into in this class are going to be built on one of those three VSEPR geometries. Yes, in Gen Chem you might have learned of a few more that give you like octahedral or square pyramidal shapes or funny things like this, ones that involve d orbitals. We're never going to run into that here. At least I can't think of a place where we will. Those are going to apply mainly to transition metal atoms in metal complexes, which we're not really going to go there. This is not an inorganic chemistry class. Good, so I think that's all I really need to say about that. We also need to point out, of course, that alcohols can undergo hydrogen bonding readily, just like water can. And that's why your smaller alcohols are either quite soluble in water or even what they call miscible in water. M-I-S-C-I-B-L-E. Miscible means soluble in all proportions. And so, but as you can imagine, as the R group attached to the OH gets larger and larger, well, then it's going to be harder for the OH groups to approach each other and either donate or accept hydrogen bonds. So if the group rather that's attached to the oxygen is very large, then you have less hydrogen bonding, and continually less and less as that group gets larger and larger. But I think that's otherwise all we really need to say about that. What else can we say about alcohols? None of this, I think, will surprise you, by the way. Like water, alcohols are amphoteric, which means they can act as either acids or bases. And if one were to treat an alcohol, I'll just go ROH here. This could be any alcohol. With a strong acid, like, I don't know, how about HCl? That's a strong acid. Well, I would expect that you would get a quantitative reaction. And one which I think the mechanism is very easy to draw, of course. It would just pick up the proton from that strong acid. You could do the same thing with sulfuric acid or whatever other strong acid you like. And you'll, of course, get, in addition to the conjugate acid of the alcohol, you'll get whatever the conjugate base of that strong acid is. But alcohols can also act as acids, as long as you treat them with a significantly, or rather a sufficiently strong base. Like, how about sodium amide? Remember that NaNH2 is NH2 minus. You have to know that in order to understand that reagent. Very, very important. And it's not the only base that's strong enough to deprotonate an alcohol. What about Grignard reagents? What about alkyl lithiums? Right, those are essentially carbanions. Those would do the job also. How about the hydride ion, H minus? Same thing. That would surely deprotonate an alcohol also. And you know those based on the pKa's of their conjugate acids. And I think you'll find for H2 and for alkanes, your pKa's are through the roof, 50 and 60 and even higher. The pKa of ammonia, which is the conjugate acid of NH2 minus, isn't quite that high, but still pretty high. As I recall, it's in the upper 30s. And with alcohols having pKa's in the upper teens, That's what tells us that this is a more than strong enough base to pull the proton off. And in the end, you will get the conjugate base of the alcohol, which is an alkoxide ion. And of course, the conjugate acid of whatever base you used. In this case, that conjugate acid would be just ammonia. But this is all just to point out that alcohols are amphoteric, just like water is. They can act as either acids or bases and will react as long as you find a sufficiently strong acid or a sufficiently strong base, which is not all that hard to do. There's a lot of room there, in other words, to find reagents that will work in either case. Good, I've already mentioned that the pKa of alcohols is of aliphatic alcohols anyway, is generally in the 15 to 18 range, round and about the pKa of water. Most simple aliphatic alcohols are a little bit less acidic than water. Maybe not much, but a little bit, maybe by one order of magnitude or so, which is small in the pKa scale, right? So much for aliphatic alcohols. What about, well, let's even write that down. Let's say pKa is round and about in the 15 to 18 range. What about phenol and substituted phenols? Well, so phenol is hydroxybenzene, and phenol is special. Phenol is significantly more acidic than aliphatic alcohols. Its pKa, and the same would be true if this benzene ring were substituted with other groups. It would still be a relatively acidic compound, but depending on what else might be attached to the benzene ring, the pKa of these guys is round and about 10, typically, give or take. And again, that's a significant difference. Remember that the pKa scale is logarithmic. So that means every notch on the pKa scale is a factor of 10. So you're talking about something that's anywhere from, what, 100,000 to 100 million times as acidic as an aliphatic alcohol. And again, I think if we look at this carefully, we can figure out why this is. Let's compare phenol to a typical aliphatic alcohol. How about ethanol? Whoops, that's an H. And again, you'd find this one is a pKa round and about 17, 18, somewhere in there. So again, it's a big difference. It's a factor of anywhere from 10 million to 100 million, somewhere in there. Now that we have these species, let's consider their conjugate bases. In other words, what we get after we remove that proton. On the one hand, you'd get actually, I'm looking ahead, I can't use a circle here. I'm gonna be drawing resonance forms, so I need to use pi bonds. I need to use Kekule structures. So that's the conjugate base of phenol. And what would the conjugate base of ethanol look like? Well, it will also have an oxyanion. So at first glance, those look like very similar species. And certainly there are similarities. But there's also a significant difference between these species. The phenolate ion, which is the conjugate base of phenol, is resonance stabilized. And again, these are not equilibria that I'm drawing. Remember what resonance means. It means that there's other ways of distributing the electrons in the structure and still getting a valid structure. So that's one. And I'll show you another. Another one of them would look much like this. And I'll even let you know there's yet a third resonance form, at least one more resonance form. I'll leave that for you guys to find. It would not be a bad exercise, but I think you'll be able to find at least one more resonance form besides these two. What's the upshot of all that? Well, that means that the conjugate base of phenol is highly stabilized by resonance. It means that the minus charge is not localized on the oxygen, but it's shared to some degree by at least 3 of the carbons in the benzene ring. So it spreads out that negative charge. And remember what we say about spreading out of negative charge. Like charges repel, so electrons repel one another. The more we can do to spread out the electron density and that minus charge, the happier it will be. The more it will stabilize it, and the less electron-electron repulsion there will be. So you have here in the conjugate base of phenol a relatively stable anion because the minus charge is delocalized. I think you would find the majority is on the oxygen, but there are significant amounts also on at least 3 of the carbon atoms in the benzene ring. Meanwhile, in the ethoxide ion, now that negative charge is localized on that oxygen, which you certainly could pick a far worse atom for the minus charge to be on than an oxygen. Oxygen's quite electronegative, so it's certainly not terrible, but it's still less well stabilized than the minus charge in the phenolate ion. So that means that the phenolate ion, I'll just make this as blunt and clear as I know how. What, me be blunt? That would never happen. Let's say the phenolate ion is happier and the ethoxide ion is less happy. If I can spell happy, boy, I'm not doing well today. There we go. Delocalized negative charge. Versus localized negative charge. So that means that when ethanol loses a proton by reacting with some base, it gives us a species that's relatively speaking less stable, less happy. Whereas when phenol loses an H+, and again, we can see what that mechanism would look like, it gets us to a species that's relatively speaking happier or more stable. So no wonder you have this big difference in pKa values. And again, memorizing the numbers isn't the issue. It would be good if you knew what they were, at least approximately, I think. But there's no wonder that we have such a dramatic difference in acidity because the conjugate bases are so different in stability. So that's a really important thing you need to know. You need to know that in order to understand relative acidities, you must think about these species' conjugate bases. You have to. There's no other way to do it. In order to understand relative acidities, you need to think about the conjugate bases of the acids in question and compare their stabilities. And I think you'll find that you can make an argument most often either involving resonance or involving the inductive effect that will make it clear which of the 2 or more conjugate bases is more stable or the most stable. But you have to think about conjugate bases in order to understand acidity. There's no way you can do it without thinking about conjugate bases. And I think that's about all I really need to say about that. I also want to point out before we begin to get into reactions, where are we at? It's 11, good. I also want to point out that thiols are significantly more acidic than alcohols as well. So I'll just use a generic thiol here. Assuming R is an alkyl group, I'm not going to, again, put my thumb on the scale by making R a benzene ring, because that will make it more acidic still. But even with R being a regular alkyl group, I think you'll find, again, these pKa's are round and about 9 or 10. And again, the argument for that is going to be to look at what happens when we lose that proton and we get the conjugate base, this thiolate ion. And so now what you have here is the minus charge is still localized on the sulfur, just like it's localized in the oxygen in an alkoxide ion. But remember, sulfur is a significantly larger atom. So instead of having this little tiny atom that has to bear the negative charge on its surface, in the sulfur, we've got this big fat atom that now you can spread the minus charge out more. So no wonder thiolates are happier than alkoxide ions. They're more stable, other things being equal, of course. You know, we want to keep things fair. But as a result, thiols are a good deal more acidic than aliphatic alcohols. Like, again, other things being equal, making sure that our comparisons are fair. And again, I think the reason why is not that hard to understand, as long as you're willing to think about the conjugate base. That's the only way to understand relative acidities. And I think that's really all we need to say about that. So that's pretty much it for properties of alcohols, phenols, thiols. I mean, we could say more, but I think that at least gives you at least the basics of the situation. In addition, today, I want to talk about how to make alcohols. We already know a bunch of ways. So we'll review those, or at least I'll show you where you can look them up. And also go over the idea of reduction of carbonyl compounds, which is another way of making alcohols. And then that will probably be it for today. Oh, I do, though, want to be sure that I announce, maybe after I turn off the recording, what to expect on Friday. I don't know that there's probably a bunch of people who have only taken exams in person so far. So just so we're clear on how it's going to work. I'll be sure to make that announcement before the end of class. Good. Questions on any of these structural or structural features or properties of alcohols and related compounds? Seems like it's fairly comfortable material, which is what I was hoping. It's largely review from Gen Chem and earlier this term, but bears repeating. Sorry, you may have said it, but the phenols and thiols are close in. Yeah, that I would say is mostly that's mostly a coincidence that they're so similar, but it is true. Phenols and thiols are generally round and about the same in terms of their acidity. Both of them are significantly more acidic than aliphatic alcohols. For different reasons. One has to do with resonance and the other has to do with just atomic size. But the idea, the underlying idea is the same. You have more stable conjugate bases than the conjugate base of an aliphatic alcohol, like ethanol. So hopefully that makes sense. Any other questions? Well, then, let's review some methods that we already know for making alcohols. So preparation of alcohols. Focusing here mostly on aliphatic alcohols, alkyl substituted alcohols. So basically what we're going to get to is some ways of making alcohol functional groups from other functional groups. We're going to learn a couple new ways, I think, by the end of the class, but there's also some ways we already know to make alcohols from other functional groups. And that's important because alcohols are really common as synthetic intermediates and synthetic starting materials. I've probably said this, but I bet if you looked at any given organic synthesis paper up to today, you would find that the vast majority of organic starting materials will be either alcohols or alkyl halides, which incidentally can at least to some degree be interconverted. But I bet that you would find that. So what are some of the ways that we already know for making alcohols? There's at least two that the book mentions, and then I thought of another that the book doesn't mention. Shame on them, I shouldn't be smarter than the book. But one of them is hydration of alkenes. So, and there's actually at least 3 different ways of doing this, right? This can be hydroboration oxidation, this can be oxymercuration reduction, or at least in cases where we don't have to worry about carbocation rearrangements, and it's the Markovnikov alcohol that we want, you could certainly just do an acid-catalyzed hydration. And those are in 8.4, if you need to review that, if you've forgotten about those reactions. What about the osmium tetroxide reaction to make a 1,2-cis diol? So it's osmium tetroxide, pyridine or tert-butyl alcohol is also fine, followed by a reductive workup involving aqueous sodium bisulfite. Well, then I would expect that you would get the 1,2-diol, and of course, in situations where stereochemistry is where different stereochemistries are a possibility, we would find the 2OH groups are cis. That reaction is an 8,7, I think. Let me just double check. Yep. And then there's yet another reaction we know from that chapter that produces an alcohol from an alkene. and that is formation of a halohydrin, where X is bromine or chlorine. And so in the end, you will get the vicinal halohydrin. And that also has an alcohol functional group, doesn't it? So that's in 8,3. So I figure that reaction deserves to be mentioned here. Good. I think that's it for, there's probably one or two others besides, but I think those are the main ones. What about other ways of making alcohols? Well, one of the most common ways besides these of making alcohols is by reduction of a carbonyl group. And so the idea behind it is going to be that there's going to be some carbonyl group, and the rest of the functional group can vary, but it will include it will be some carbonyl containing functional group. And I'll do reduction, which, by the way, if you ever see H in square brackets, let's just take care of those abbreviations. This just means that a reduction has taken place. It's kind of shorthand for generically a reduction has taken place. The opposite of that is, that you might see, is O in square brackets. That means that an oxidation has taken place. And certainly we can still say more about how to know whether it's a reduction or an oxidation, or, which is another possibility, which is that a reaction could be neither oxidation nor reduction. Those happen also. Not every reaction is redox. So we can reduce carbonyl compounds and get products that look something like this, that are alcohols. And again, the other two substitutions in the carbon can vary. So we just need to learn what some of these reagents are that will do this for us. One possibility, but basically what we'll learn is that aldehydes can be, I'll write this down, don't worry. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols. So being a little bit less generic about this, let's say that we started with an aldehyde. What we'd find is that reduction of that aldehyde gives you a primary alcohol, RCH2OH, in which one of the new hydrogens is going to come from our reducing agent, and the other, the one that's in the oxygen, we'll learn probably comes during the workup step. That's going to come from water or H3O plus or something similar. And likewise, if we started with a ketone instead of with an aldehyde, well, then we'd find after reduction that our product is going to be a secondary alcohol. And there will, in all cases, be inorganic side products as well that we don't really so much care about. So all we need to learn now is what are these reagents that will do that for us. And there's two that are by far the most common. One of them is sodium borohydride. That's going to be the less reactive one. I think you might actually do a sodium borohydride reduction. If not this term, then maybe next term in lab. And the other one that's much more reactive is lithium aluminum hydride. And the reason for the difference in the reactivity between these two reagents is because of mainly because of the difference in polarity of the bonds from hydrogen to that central atom. So let me make sure that we're clear on what the structure of these things is. So the BH4 minus ion, the borohydride ion, looks like this. And of course, there's a sodium ion that's a countercharge. And lithium aluminum hydride looks at first glance very similar, same type of structure. Aluminum is, of course, right below boron in the periodic table. But aluminum hydrogen bonds and boron hydrogen bonds are not created equal, because aluminum is a good deal more metallic than boron is. Aluminum is a metal, boron is a metalloid. So you're going to get far more polar aluminum hydrogen bonds. So no wonder that one is so much more reactive. In both cases, the alkali metal ion doesn't play a role in the reaction. That's just a spectator ion. I could not tell you why it's sodium borohydride and lithium aluminum hydride. I know you can get lithium borohydride. I'm pretty sure you can get sodium aluminum hydride. So, but I don't know why those metals are chosen. As far as I know, though, the identity of the alkali metal ion doesn't really matter. It's the anion that's going to do the work for us. These are both sources of the hydride ion. So you can think of both of these as being able to expel H minus like this. So, and we're actually not going to learn the mechanisms. You won't be responsible for the mechanisms of these reactions yet. We'll eventually learn them in round and about chapter 19 next term. But these both act as a source of the hydride ion, which is H minus. So please be sure that you distinguish in your mind very carefully between H minus and H plus. They are very, very different critters, right? H minus is a very strong Bronsted-Lowry base and also a pretty darn good Lewis base or nucleophile, whereas H plus is acidic. So please be sure you understand the difference between those two. And we'll go more into detail about how these work next term. But, you know, you can basically consider both of these as sources of the hydride ion, with lithium aluminum hydride being more reactive than sodium borohydride. And when it comes to aldehydes and ketones, these two are interchangeable. And maybe we'll get to, maybe by the end of the class, we'll get into some cases where they're not interchangeable. And if not, we'll cover it on Monday. It's not the end of the world. Good. So what else was I going to say about that? So in a typical, let me just pick, let's do benzaldehyde as a typical carbonyl compound. And let's say we wanted to make benzyl alcohol. We have two ways of doing it. So the product with either sodium borohydride or lithium aluminum hydride will be benzyl alcohol. So apart from the mechanism, the way you get the structure of the product is by following this step-by-step method. Step one, well, actually there's only one step. Turn C double bond O into C single bond OH. So C double bond O into C single bond OH. Actually, I lied to you, it is two steps after all. Then you'll find the resulting carbon is only 6 electrons around it, so stick another hydrogen on it. And that's in the class notes, by the way. I gave you that step-by-step method in the class notes. So turn C double bond O into C single bond O, and then you'll need one more hydrogen in order for a carbon to obey the octet rule. And again, those steps are in the class notes. You don't need to worry about that. We'll get more into the details about the mechanism next term. So, but again, either sodium borohydride or lithium aluminum hydride will do that for us. If we wanted to do this with sodium borohydride, this is typically done by adding everything together. Usually you add the sodium borohydride, and the solvent is generally a mixture of a small alcohol, either methanol or ethanol, and water. So I'll put CH3OH in water, though that could just as easily have been ethanol and water. And in general, you want to mix all those things together. Now, both methanol and water, and ethanol also, by the way, all of those will react slowly with sodium borohydride. But the reaction is very slow, and sodium borohydride reacts very much more quickly with the carbonyl compound. So you're fine. And you can follow that up with an acidic workup step if you really wanted to. Sometimes you don't even. What I sometimes see them do in undergrad labs is they just have you boil it for a while. You know, get the solvent boiling, and that will work the reaction up, and then you can isolate your alcohol product. So it's typical for everything to be all in the same solution for sodium borohydride. We can't do that with lithium aluminum hydride. It's too reactive for that. So let me show you how that would look. Actually, I'll even pick a different compound. So I do want to stress that this starting material can be a ketone or an aldehyde. This one also can be a ketone or an aldehyde. I just happened to pick an aldehyde up here. And I'm going to pick a ketone over here. But you could do it either way. In this case, let's choose, how about 3-hexanone as our starting material? But you could choose either sodium borohydride or lithium aluminum hydride for either of them, and you'll get the same result. So for aldehydes and ketones, these two reagents are interchangeable. That's not going to be true, as we'll find, as I'll probably at least introduce today, but we might need to do some more detail on that on Monday. But that's not going to be the case for carboxylic acids and esters. There, these two reagents will not be interchangeable. But for aldehydes and ketones, you can use either set of reagents. But if you want to use lithium aluminum hydride, what you need to know is that it's a two-step process. In the first step, we add lithium aluminum hydride, generally in some kind of ether solvent. Diethyl ether is very typical. You could also use THF, tetrahydrofuran, or some other ether solvent, but you need that solvent to be aprotic, because protic solvents react violently with LAH. Remember, it's going to give H-, which is an exceedingly strong base. And so once that pulls a proton off of a protic solvent like ETOH or water or whatever you like, you get hydrogen gas, and the hydrogen gas ignites because there's so much of it produced so quickly. And something that I have a great deal of difficulty convincing students in, always have, all these years I've had trouble convincing students, is that fires are bad. Fires are a bad thing. And that's probably because I've had multiple fires that I didn't intend to have. But anyway, so we need to use an aprotic solvent for lithium aluminum hydride. And we're going to add, generally what you'll do is you'll dissolve your ketone or aldehyde in diethyl ether. You'll probably cool it down somewhat since the reaction's quite exothermic. Please tell us an accidental fire story. If there's time, I will. Although I have to be honest, I wasn't using LAH. I've always been careful enough with LAH that I've never had a fire. But be that as it may, the way I normally do it, lithium aluminum hydride is a solid, it's a powder. So I would just pitch it in little by little using a spatula and then let it stir for a while. There are ways of testing if your reaction is done. And then only after everything is done reacting, then you work the reaction up. And you can put either H2O or H3O+. Either of them would be fine. But we work that reaction up very, very carefully. So what do I mean by workup? Well, the workup step in a reaction is something pretty commonly done so that we get, so that two things occur. First of all, if there's any excess nasty reagent, some inorganic nasty reagent, we need to destroy all that so that we can isolate our compound easily. So there's probably going to be a pretty goodly excess of lithium aluminum hydride. We need to neutralize that or destroy it. And so that's why we add something protic, like water. The other thing that's often the case is, and we'll see this when we learn the mechanism of these reactions, is that at first we won't get our neutral product out. We'll get something ionic. And so generally, the initial product here would be CH2O-. And likewise, here you would get your secondary alcohol. And at first, again, you would get O-. So we need to put that proton back on so that we're isolating a neutral compound. That's something important that you need to know. In general, you're aiming to get a neutral compound out of it, not an ion. And so these so-called workup steps generally will do both of those things for us. They can involve proton transfers, or they can involve some other, like here we've got, with the osmium reaction, here our workup step is a reducing agent. So generally what you want to do is add the chemical opposite of whatever the main reagent is. Here with LAH, you've got yourself a very, very strong base, H-. So we'll add a relatively mild acid. And I'll tell you, that story I can certainly have time to tell you is how I generally work up LAH reactions. I've done a bunch in my life. Here, with osmium tetroxide, this is now a very strong oxidizing agent. That's osmium in the +8 oxidation state. Very, very strong oxidizing agent. So that's why we need a reducing agent to work the reaction up. So generally you add mild bases if your reaction solution is very acidic, mild acids if it's very basic. You add a mild reducing agent if you're using an oxidizing agent, and so forth. It's very commonplace with workup steps to add the chemical opposite. And I think if you go back and look at some of your Chem 237 labs, those of you who are taking lab, you'll find that you've probably already done multiple workup steps. Maybe they just didn't make a big deal about it. Good, so I've done a fair few LAH reactions in my life, not because I'm so great, but because it's just so commonly used. And the way I really love to work up an LAH reaction, I told you what I've done so far. I dissolved my ketone or aldehyde in diethyl ether, cooled it down, pitched in by little bit my LAH that I had weighed out. And then I'll wait. These things don't usually take very long, an hour maybe. And when I've tested that my reaction is done, which there's ways of doing that, the way I really like to work up these reactions is I will pitch in little pieces of ice very carefully. And the reaction, even still, is exceedingly violent. Bubbles like you wouldn't believe. And those bubbles are hydrogen gas. So if there's a spark anywhere, it's a problem. But eventually you'll see the bubbling start to cease. And that's when you can get out your separatory funnel and do your extraction. But you have to be very, very careful working up LAH reactions. And that leaves me with 7 minutes. Good. I think I would sort of like to leave esters and carboxylic acids until next time. Let's see. So I just want to say that, again, for aldehydes and ketones, these two sets of reagents are interchangeable. Doesn't matter what you use. They will both give the same result. You'll reduce an aldehyde to the corresponding primary alcohol, a ketone to the corresponding secondary alcohol. On Monday, we'll learn, though, that these two sets of reagents are not interchangeable for esters and for carboxylic acids. But we can leave that until Monday. I think that leaves me time for a quick fire story. And then maybe I'll pose, let's look at sort of an SN1, E1 type question, maybe even a slightly complicated one. It occurred to me on my way over here, and I don't even know how I could phrase this to put it on the exam. I'd have to take only a part of it, maybe. But be that as it may, I haven't had an LAH fire, but I have had a hydrogen fire. I wasn't using LAH, but I was using, I think, sodium hydride. And I had just started graduate school. I was in maybe my second year of graduate school. And I was kind of dumb, even more so than today, if that can be believed. And so I figured, well, if I can use water or ice to neutralize calcium hydride, then surely sodium hydride will be fine also. No. So it gives off a lot of hydrogen and a lot of heat also. And what happens is then the hydrogen ignites. And after that, any organic solvents burn as long as they're flammable. During all this time, there's nothing that you can do. So there's this big fire raging in my hood. And again, there's nothing you can do. When there's nothing left to burn, the fire goes out. And that's exactly what happened. It took maybe 45 seconds or something. But it was pretty terrifying. And I remember a very senior graduate student sort of standing behind me, looking over my shoulder going, oh, look, not helping at all because he can't help. And, it was pretty funny. Anyway, looking back on it, it was funny. But at the time, I was pretty terrified. Good. So let's consider what would happen. I just thought of this compound literally walking over here from my car. Let's say that we took this tosylate and we just heated that up in ethanol. What kind of result would you expect? This is again a rather intermediate case, which are a little bit harder to ask exam questions on, because I think we can expect a mixture. You've got a secondary substrate, and we're heating this in a protic solvent. So I don't think we're going to get any kind of bimolecular reaction. I don't think we're going to get very much SN2. I think we're going to be getting mainly SN1, and what else? Maybe some E1, right? Because we said that SN1 and E1 often compete, and especially with these right down the middle secondary substrates. If this were a tertiary substrate, then I think we'd be largely looking at SN1 and E1. And again, we will probably get both. So how do you know what the products will look like? Well, in order to get the nucleophilic substitution product, which I again think would mainly come in an SN1 fashion, possibly a teeny bit of SN2, you look where your leaving group is, and you replace that with the solvent as the nucleophile. And of course, this would initially be protonated. We'll get to the mechanisms also, time permitting, but that will initially be protonated, and then will get deprotonated by another ethanol molecule. And I think this will mainly be the SN1 product, maybe a teeny bit of SN2. Not that it really matters, because you'll get the same thing in either case. Notice that I very carefully picked a starting material that's not chiral. So there's no stereochemical issues here. That certainly makes things a lot easier. I'm not gonna commit to doing or not doing a particular thing in the exam, but I figured this would make something useful for us to look at. And then what would the E1 product look like? Well, in order to get that structure, you look where your leaving group is, and remember, you need to find a proton on one of the carbons next door to the one that bears the leaving group. And it doesn't matter, all four of those protons are the same. So we'll pull one of those off, we'll lose our leaving group, and you'll get a double bond. You could also have drawn the double bond here. It's the same compound. So I think that's going to be your E1 product. So what would the mechanisms look like? Well, I think the first step is going to be the same for both. We'll lose our tosylate ion, and we'll get a secondary carbocation. And I can't really think of a good way for that carbocation to rearrange. I think if you do a hydride shift, you'll get another secondary carbocation. So there's no real driving force for that to happen. After that, ethanol will attack. And again, you'll notice I'm not using ethoxide ion. The reason I know not to do that is when I look at what I'm given, I don't see any. I don't see any NaOH or something like that, right? And ethanol is not a strong acid, so you're not going to get any significant amount in solution of the ETO minus ion. Maybe 1 in 10 to the power 20 molecules or something like that. Not worth considering. And so at first, you'll get the conjugate acid, and then we'll need another ethanol molecule, which we have in abundance, that will pull off the proton for us, and that would be our SN1 product. It might sometimes be that an ethanol molecule will come in and kick out the tosylate ion and go straight to this. That might sometimes happen. It doesn't really matter though, because it's the same thing. And that's not unusual for nucleophilic substitution reactions that can go either way. What about the E1 product? Well, again, we lose our tosylate ion. Again, we get our carbocation. What am I doing? And the only difference being in this case, we'll pull off one of these 4 protons. It doesn't matter which. We'll use an ethanol molecule to do that, and we'll get our elimination product. So I think that will happen in 2 steps. That will be our E1 product. Again, those 2 molecules are the same. So I'm just showing you sort of how you can analyze different situations using the ideas from the flow chart that I gave you. So this is a case where I think you might get both. You've had 3 of my exams, not to mention you have an old exam available online, but I think my reputation is pretty well deserved that I do my best to make it clear what you need to do to get credit. At least people tell me my questions are better than OWL questions, which, again, that might be what one of the British poets called damning with faint praise, but if faint praise is all I can get, I'll take it. In terms of what's going to happen on Friday, basically, don't come here. You'll just zoom in, just like always. And at 10:40, the exam should drop on eCampus in the same place as you would get class notes or old exams or like that. And you'll download it. If you have a printer, you'll print it out. If you don't, it doesn't matter. You can write out your answers separately. And this will all be in the instructions, by the way. So you don't have to copy down all of the questions. All you really need is your answers. When you're done, you'll scan it in, or if you have a scanner, or people are, I think, largely just taking pictures with their cell phones. And then you'll need to use one of these apps that I sent out, examples of apps that can convert into PDFs for you. You'll have 55 minutes to take the exam, and then I generally add on another 20 to give you time for printing out and taking pictures and converting to PDF and submitting on eCampus. Be prepared for the submission process on eCampus to be kind of a pain. eCampus kind of clogs up sometimes, so I'm going to give you at least 2 attempts for submission. You may need to use both of them. After that, certainly check your submission to make sure that everything made it through. My strong preference is that everyone submit to eCampus if at all possible. If all else fails, then you can email it to me. But please try multiple times to submit to eCampus if necessary, and please be patient. And in general, it works out pretty well. And I am well over time, so I will let you all go, and I will see you not here. I will see you on screen on Friday. Have a good day.